The power equation demonstrates that the small resistor accounting for the internal resistance of the primary windings will consume approximately 235.3 millivolt amperes of apparent power, all of which is being directed towards 235.3 milliwatts of real power and none of it towards a reactive interchange. This isn't a terrible loss to the system and may only result in a small temperature rise. The power equation additionally demonstrates that the resistance accounting for iron losses associated with eddy currents will consume 1.8 volt amperes of apparent power, all of which is being directed towards 1.8 watts of real power and none of it towards a reactive interchange. Again, this isn't a terrible loss to the system and may only result in a small temperature rise. Similarly, the power equation demonstrates that the inductor accounting for both magnetizing current and hysteresis will consume 7.1 volt amperes of apparent power, none of which is being directed towards real power, and all positive 7.1 bars is being directed towards a reactive interchange. As previously, this reactive power is necessary for the operation of the transformer and really doesn't affect the efficient transfer of real power. Finally, the power equation demonstrates that the reflected impedance will consume only 55.7 volt amperes of apparent power, all of which is being directed towards 55.7 watts of real power and none of it towards a reactive interchange. This is where we took a hit. Because both applied voltage and current went down, the reflected impedance consumes less power than previously. Let's calculate total apparent power input to the transformer. First, total power is the sum of individual apparent powers. Additionally, total apparent power is the complex conjugate of primary voltage times primary current. Either method yields a total apparent power input of approximately 58.2 volt amperes, 235.3 milliwatts goes to the small resistor accounting for the internal resistance of the primary windings, 1.8 watts of which goes to the parallel resistance accounting for iron losses associated with eddy currents, positive 7.1 bars of which goes to the parallel inductor accounting for both magnetizing current and hysteresis, and finally 55.7 watts of which goes to the reflected impedance. Now I've got a good picture of the input, let's take a look at the output. Given the voltage applied to the primary winding, this is not the full 120 volts as previously, but rather only 119.5 volts. The directly proportional turns ratio relationship demonstrates that the secondary voltage will only be 23.9 volts. Using the voltage divider rule, it can be demonstrated that the 10 ohm resistive load will experience a voltage drop of approximately 23.3 volts at an angle of 0 degrees. Similarly, using the voltage divider rule or Kirchhoff's voltage law, it can be demonstrated that the small resistor accounting for the internal resistance of the secondary windings will experience a voltage drop of approximately 583.0 millivolts at an angle of 0 degrees. As we anticipated, the small resistor accounting for the internal resistance of the secondary windings does experience a voltage drop. However, it's not that much. This being said, it will still dissipate a small amount of real power considered a loss to this system. More importantly, the inclusion of the series resistance accounting for the internal resistance of the secondary winding again shows that not the full voltage will be dropped across the load impedance. Ohm's law demonstrates that the series combination of the small resistor accounting for the internal resistance of the secondary windings and the load impedance will draw roughly 2.3 amperes of current at an angle of 0 degrees. Let's now examine power. The power equation demonstrates the small resistor accounting for the internal resistance of the secondary windings will consume 1.4 volt amperes of apparent power, all of which is being directed towards 1.4 watts of real power and none of it towards a reactive interchange. This isn't a terrible loss to the system, may only result in a small temperature rise. Similarly, the power equation demonstrates that the load impedance will consume 54.4 volt amperes of apparent power, all of which is being directed towards 54.4 watts of real power and none of it towards a reactive interchange. You note a roughly 1-to-1 correspondence between the power consumed by the reflected impedance and the series combination of elements on the secondary. Our previous calculations using reflected impedance demonstrated a consumption of 55.7 watts of real power. Accounting for rounding imperfections in the secondary, you'll note the summation of power consumed by both the load and the series resistance is also roughly 55.7 watts. More to the point of this particular lecture is the efficiency of this larger system with respect to the transfer of real power. You note real input to the primary side of this transformer is 57.8 watts. However, the small resistor accounting for the internal resistance of the primary winding weighs 235.3 milliwatts. The parallel resistance accounting for iron losses associated with eddy currents lets 1.8 watts slip through its fingers. The small resistor accounting for the internal resistance of the secondary windings drops 1.4 watts on the floor, leaving only 54.4 watts of usable power output for the load. Accounting for all of these losses, this transformer can now be said to be 54.4 over 57.8, or only 94.1% efficient. We're not 100% efficient, however, we are still really close. This non-ideal transformer would dissipate these small losses as heat, and as such, might exhibit a small temperature rise. Notably, this more sophisticated model of a non-ideal transformer accounted for an important property, that being the tendency of a transformer output voltage to fluctuate given different load requirements. In our ideal situation, we applied 120 volts and got 24 volts out. However, this increasingly sophisticated model, you'll note of the 120 volts applied to the primary, only roughly 119.5 volts got there because of the small voltage drop across the small resistor, accounting for the internal resistance of the primary windings. Additionally, of the roughly 23.9 volts applied to the secondary winding, only roughly 23.3 volts appeared across the load because of the small voltage drop across the small resistor accounting for the internal resistance of the secondary windings. Here's the important part. Given a reduction in applied voltage across a load, current through the load decreased. Given power is the product of reduced voltage and reduced current, power delivered to the load decreased. Can you now dig the disproportionate influence the winding resistance has on the performance of a transformer? Our original ideal transformer model consumed 57.6 watts from the source, and the load got 57.6 watts. Using this more sophisticated model, the transformer isn't even consuming the same amount of power, but rather it's consuming 57.8 watts, of which only 54.4 watts gets to the intended destination. We'll examine this behavior in a moment in terms of transformer voltage regulation. Before doing so, I'd like to do a quick practical example of these non-ideal principles in the form of an illustrated example that you can make as simple or as hard as you want. My simple question to you is this: which is the better transformer? Transformer A or Transformer B? They're both 1 to 2 step-up transformers powered by 120 volts supplying current to a 400 ohm load resistor. Transformer A has the following properties. The internal resistance of the primary windings is 0.2 ohms. The parallel inductor accounting for both magnetizing current and hysteresis has a magnitude of 4 kiloohms. The parallel resistance accounting for iron losses associated with eddy currents has a magnitude of 10 kiloohms. And finally, the internal resistance of the secondary windings is 0.1 ohms. Transformer B, in contrast, has the following properties. The internal resistance of the primary windings is 5 ohms. The parallel inductor accounting for both magnetizing current and hysteresis has a magnitude of 1 kiloohm. The parallel resistance accounting for iron losses associated with eddy currents has a magnitude of 2 kiloohms. And finally, the internal resistance of the secondary windings is 2 ohms. Transformer A appears to be made out of high-quality materials, notably thick, highly conductive wires, and the core is made out of an exotic metallic glass alloy. Transformer B, in contrast, appears to be made out of lengths of twisted-together coat hangers wrapped around a core of compressed cheese. It even has flies circling around it and some sort of foul-smelling goo leaking out of it. The answer to this question is quite obviously Transformer A is better than Transformer B because of several easily identifiable properties. First, the windings of Transformer A have less internal resistance than Transformer B, meaning they will experience less of a voltage drop, waste less power, and as a result, the load will experience more of a voltage drop and receive more power. Additionally, the parallel resistor accounting for iron losses associated with eddy currents has a larger magnitude, meaning it presents less of a leakage path, and as a result, less power will be wasted. Finally, the parallel inductor accounting for both magnetizing current and hysteresis also has a larger magnitude, and as such will draw less current, meaning Transformer A necessitates the consumption of far less reactive power to operate than Transformer B. Conversely, the windings of Transformer B have more internal resistance than Transformer A, meaning they will experience more of a voltage drop, waste more power, and as a result, the load will experience less of a voltage drop and receive less power. Additionally, the parallel resistor accounting for iron losses associated with eddy currents has a smaller magnitude, meaning it presents more of a leakage path, and as a result, more power will be wasted. Finally, the parallel inductor accounting for both magnetizing current and hysteresis also has a smaller magnitude and as such will draw more current, meaning Transformer B necessitates the consumption of far more reactive power to operate than Transformer A. In summary, Transformer A is better than B because its series irregularities are smaller and its parallel irregularities are larger. To put it another way, Transformer B is worse than A because its series irregularities are larger and its parallel irregularities are smaller. In fact, that's largely the reason behind the simplified model of an ideal transformer. An ideal transformer has no resistance in series with its windings, and the parallel irregularities are so large, leakage paths don't exist. As we previously demonstrated, even accounting for these irregularities, transformers are still astoundingly efficient. At efficiencies approaching greater than 95%, oftentimes you're more than justified in skipping all the complicated series parallel circuit analysis and simply assuming the transformer is ideal. Before we move on, allow me to comment on the efficiency of non-ideal transformers during no-load conditions and expound upon some of the approximations we made earlier. Ordinarily, we'd expect a device that's not doing anything to consume no power. Consider a 60-watt light bulb modeled as a 240 ohm resistor. Everyday experience tells us that when the light bulb is off, it draws no current and consumes no power. In contrast, when the bulb is on, it draws 500 milliamperes of current and consumes 60 watts of power. Consider, however, a non-ideal 5-to-1 step-down transformer powered by 120 volts AC, supplying current to a light bulb modeled as a 9.6 ohm resistance. When the switch controlling the light bulb is open, will this system consume power? Keep in mind, no current is flowing in the secondary winding and the bulb is not illuminated. By all means, pause the lecture and think about this. If you're tracking, you should have come to the following conclusions. Recall that the model of a non-ideal transformer includes leakage paths in parallel, and these leakage paths are in parallel with the reflected impedance. If the switch is open on the secondary, the reflected impedance is infinite and no current will flow through this path. This being said, the leakage paths, specifically the resistor accounting for iron losses associated with eddy currents and the inductor accounting for both magnetizing current and hysteresis, will continue to draw current. This explains the origin of the term excitation or magnetizing current if you were wondering about it earlier. Even when the transformer isn't powering a load on the secondary, the primary continually draws current. Importantly, note any current drawn by these leakage paths must also travel through the primary winding, and as such, the more current drawn, the more power will be dissipated by the resistance of the primary windings. Higher quality, extremely efficient transformers have large magnitude leakage paths, and as such, draw less current and waste less power in the standby mode. Consider our earlier approximation of a non-ideal 5-to-1 step-down transformer powered by 120 volts AC, where the internal resistance of the primary windings is assumed to be 1 ohm, the parallel resistance accounting for iron losses associated with eddy currents has a magnitude of 8 kiloohms, and the parallel inductor accounting for both magnetizing current and hysteresis has a magnitude of 2 kiloohms. Let's examine the performance of this non-ideal transformer with no load on the secondary. When no current is flowing in the secondary winding, the reflected impedance path is infinite. However, leakage paths in the primary continue to draw current. The parallel combination of the resistor accounting for iron losses associated with eddy currents and the inductor accounting for both magnetizing current and hysteresis has a combined impedance of roughly 1.9 kiloohms at an angle of 76 degrees. Given this combined impedance is in series with the resistor accounting for the internal resistance of the primary windings, Ohm's law demonstrates this non-ideal transformer will draw 61.8 milliamperes of current at an angle of negative 76 degrees, even when no load is being powered on the secondary. Can you dig the heavy implications of this simple calculation? Transformers always draw current, even when they're not providing power to a load. Now, before you freak out about this, take note of the large lagging phase angle, characteristic of a reactive element that merely exchanges reactive power with a source and largely doesn't consume real power. This being said, it's not lagging by a full 90 degrees. We might expect consumption of a small amount of real power. The power equation demonstrates that the non-ideal transformer consumes 7.4 volt amperes of apparent power, approximately 1.8 watts of which is directed towards real power, and approximately positive 7.2 VARs is directed towards a reactive interchange. As we expected, a majority of apparent power is going towards reactive power, its destination being the inductor accounting for both magnetizing current and hysteresis. However, a small amount of real power is continuously being dissipated in the resistor, accounting for iron losses associated with eddy currents, and a very, very tiny, almost negligible amount of power would be dissipated in the resistor, accounting for the internal resistance of the primary windings. In summary, non-ideal transformers performing absolutely no measurable amount of real output always consume a relatively constant amount of reactive power and a small but measurable amount of real power. If you think about it, despite all my earlier enthusiasm about their usefulness and relative efficiency in the loaded condition, an unloaded transformer on standby is probably the single most inefficient device in the world because it continually consumes power and contributes absolutely nothing. Does this remind you of a certain lab partner? Now, 1.8 watts might not seem to be a lot of wasted power, but given energy is power times time, think about how this adds up over time for a large population. Consider a nation comprised of 323.1 million knuckleheads, where each person owns a single device that continually wastes 1.8 watts of power. In a single 24-hour day, each device wastes only 43.2 watt-hours of energy, a relative drop in the bucket. However, the entire nation of 323.1 million people wastes 13,957,920 kilowatt-hours of energy. Assuming an energy price of 12 cents per kilowatt-hour, this nation effectively wastes almost $1.7 million every single day doing absolutely nothing. Can you now dig the seriousness of this problem on a large scale? The fundamental problem with our existing circuit is the location of the switch. As currently implemented, opening and closing the switch only cuts current in the secondary and not the primary, leaving the non-ideal transformer and all its modeled inefficiencies, including leakage paths in parallel, still active. A far better re-engineering of this circuit might be to relocate the switch to the primary side, effectively cutting the head off the snake by completely depowering the transformer in addition to the load in the secondary. Moving on. As you're no doubt aware, any reduction in voltage reduces current, and power, being the product of voltage and current, will take a double hit. This is perhaps the larger point of the preceding section. Yes, efficiency, even for crappy transformers, is respectably high. However, output voltage isn't constant for a non-ideal transformer, accounting for imperfections. A key transformer performance characteristic is known as voltage regulation, being a measurement of how close a particular transformer can keep output voltage to ideal conditions for a range of loads. A transformer with poor voltage regulation might be a deal breaker for an application that necessitates a relatively constant supply voltage. Means of calculating voltage regulation vary. However, it's often calculated as the ratio of the difference in output voltage at no load and full load conditions over the output voltage at full load conditions, and typically expressed as a percentage. Consider a 5-to-1 step-down transformer powered by 120 volts AC. If this transformer was ideal and truly 100% efficient, the secondary output voltage would always be 24 volts regardless of current demand on the secondary. This is obviously too good to be true. Real transformers exhibit a small reduction in output voltage as current drawn by the load increases. The origin of this voltage drop is the small but measurable resistance of both the primary and secondary windings internal to the transformer. In a sense, voltage regulation is a current-dependent phenomenon that occurs in two stages. Recall we earlier observed current drawn by the reflected impedance and the parallel leakage paths must travel through the resistor, accounting for the internal resistance of the primary windings, and as such, a small voltage drop occurs. This means that the transformer primary windings internal to our model never receive full voltage, and the more current flowing in the primary, the larger this departure becomes. With respect to the secondary, any current drawn by the load must travel through the resistor, accounting for the resistance of the secondary windings internal to the transformer, and as previously, a small voltage drop occurs. Externally, this means that the load never receives the voltage of the secondary, and the more current flowing through the secondary, the larger this departure becomes. This double internal voltage drop manifests itself external to the transformer as a reduction in output voltage as current drawn by the load increases. Consider the following performance data for a non-ideal 5-to-1 step-down transformer. The primary winding has a rated voltage of 120 volts and a current rating of 1 amp. The primary winding can therefore be considered to have a power rating of 120 volt amperes. The secondary winding has a rated voltage of 24 volts and a current rating of 5 amps. The secondary winding can therefore be considered to also have a power rating of 120 volt amps. As we vary the impedance on the secondary, we observe the following properties. When no current is being drawn from the secondary, the transformer appears to have an output voltage of 24 volts, as one might expect. The primary is drawing only the relatively small excitation current, and there's no current flowing in the secondary, so there's no internal voltage drop in the secondary. When 1 amp of current is being drawn from the secondary by the variable load, the transformer appears to have an output voltage of 23.86 volts. The primary is drawing slightly more current, as is the secondary, and now there's an internal voltage drop in the windings. This being said, is 23.86 volts a cause for concern? Not really. We're still super close to the ideal 24 volts. However, we're already seeing a dip in output voltage at 1/5 the secondary winding rated current. Just like your lab partner's personal hygiene, this can only get worse as time goes on and things heat up. When 2 amps of current is drawn from the secondary by the variable electrical load, the transformer appears to have an output voltage of 23.72 volts. Output voltage again slightly dropped at this condition of increased current demand. When 3 amps of current is being drawn from the secondary by the variable electrical load, the transformer appears to have an output voltage of 23.58 volts. Output voltage continues to drop. When 4 amps of current is being drawn from the secondary by the variable electrical load, the transformer appears to have an output voltage of 23.44 volts. Output voltage continues to drop. Finally, when 5 amps of current is being drawn from the secondary, the rated current, and our cutoff for this experiment, the transformer appears to have a final output voltage of 23.3 volts. Looks like the difference in output voltage between no load and full load conditions is 0.7 volts. Using the voltage regulation formula, it can be said that this transformer has a voltage regulation of roughly 3%, which is okay. Most commercially available transformers try to stay below the 3% dividing line, depending upon application. Obviously, a large power transformer supplying a city or a factory needs to have extremely good regulation below 3%, so output voltage remains steady and predictable despite varying demands. However, ironically enough, transformers with poor voltage regulation above 3% do have their uses. Consider a load that changes impedance as it warms up. This load might require an initial high startup voltage, and as time goes on and current demand increases, voltage can drop. Alright, that's about it for non-ideal transformer analysis. In conclusion, this lecture examined increasingly sophisticated models accounting for inefficiencies of non-ideal transformers. We examined copper losses in the form of internal resistance to the primary and secondary windings, explained magnetizing or excitation current, discussed iron losses in the form of hysteresis and eddy currents, and finally we examined efficiency, voltage regulation, and the less than ideal performance of a transformer with no load in the secondary. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.